Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 28. So, we are discussing about this fluorescence anisotropy, and as you can see here in our previous discussion. So, basically what you are going to measure? You are going to measure the intensity in the detector, right. So, and this intensity in the detector should be multiplied, that VH part, IVH part should be multiplied with the this factor G factor, which is nothing but the sensitivity of the detector for the differently polarized light. So, I can write here. So, R should be equal to I VV minus G I VH divided by I VV plus 2 G I VH. So, these are the quantity which is measurable in the detector, right, and this G value will find out from the horizontally polarized excitation light source. Now, if I write, I can also write this as equal to I parallel minus I perpendicular, because this is that original value I parallel plus 2 I perpendicular, because this is the original value, this is before reaching the monochromator. After reaching the monochromator, it become VH and VV, right. So, this become VH and this become VV, and there is all the problem, right, the sensitivity problem. So, I put this G, but generally we do not care so much, and we always write G over here 2 G I perpendicular, we generally do not care. So, it looks like that this is actually the measured intensity at the detector, but actually the measured intensity at the detector is this one IVV, IVH, IHV, IHH, like that, but we generally do not care. So, in most of the book what you will see, it is written that I parallel minus G I perpendicular divided by I parallel plus 2 G I perpendicular. Assume that this is the measured intensity in the detector, this is not the intensity just after the emission, after the sample cell, not that, it is the measured intensity. But I can also tell, if I say it clearly, then it is okay to write these things. If I do not say clearly, then it is not okay to write that. Okay. Okay. So, let me write this one. Now, my question is that what is the time dependency of this? I have started with time dependency. I said that I will excite this sample with the delta pulse excitation. All the fluoropores whose transition moment is parallel to the electric field of the excitation light source, that will be preferentially excited to the excited state, and the excited state will be polarized emission, will emit the polarized emission. As time goes, the molecule will reorient themselves, right. Originally it was excited like this way, now as time goes molecule will reorient like this way or that way or this way, whatever the ways, right. The molecule will reorient themselves, and if the reorientation time is less than the lifetime, then after the molecule will reorient, you will get the emission from those molecules. So, then emission will be unpolarized emission, right. So, I will go from the situation excited state is anisotropic to excited state is isotropic, orientationally isotropic. So, if I want to measure the time dependency, right, and then I change it to the CW mode, now I want to again come back to the time dependency, right. So, if I want to again come back to the time dependency, this equation R equal to I parallel minus G I perpendicular, that equation I can simply write as in function of time. So, here R will be the function of time, that will be I parallel will be a function of time, minus G is not a function of time, G is fixed for a particular instrument, because it is the sensitivity of the monochromator and the detector towards the horizontally and vertically polarized sample, the difference, the ratio of the sensitivity. So, G I perpendicular, this is a function of t divided by I parallel, which is a function of t, plus 2 G I perpendicular, which is a function of t. Now, if I now calculate this R value at time 0, let us say just after excitation, the R value should be more. As time goes, this R value will keep on decrease and decrease and decrease, and at a longer time, very long time, right, as I said that probably all the fluorophore will reorient themselves and it will be randomized, right. So, then the then the fluorescence will be unpolarized completely and you will get the R equal to 0. So, looks like that if I now plot the RT versus T, it should start from a high value, right, and from looking at this equation it looks that the value should be equal to 1 and then it will go to 0, right, when I parallel equal to I perpendicular, then the value will go to 0, right. Let us now see this exact form of this I parallel T, I perpendicular T, and let us now try to find out what will be the functional form of our T. For that, let me imagine that I have a number of molecules in my solution, and for a arbitrary polarization of excitation, that arbitrary polarization of excitation could be along x axis, could be along y axis, could be along z axis. So, I will not specify right now, I will specify it later, but for any arbitrary polarization of excitation, I can write the intensity of each direction, how the intensity will vary with time. The variation of intensity with time for every direction, I have the 3 directions here, right, either x or y or z. So, let me write these things over here. For this I x, which is a function of time, the d dt of that, how this is changing with time, right. If now consider the molecules which is in the excited state is like, let us say this is my x axis. So, the molecule is like this way. So, simply the molecule will come back from the excited state to the ground state. So, the intensity along this axis will decrease. So, if I have d dt of the I along a x, right, I should have a rate constant of deactivation, from the excited state to the ground state, and that should be the negative multiplied by the concentration this fluorescence intensity along the x direction. So, I have this, what is that? Rate constant is Kr plus Knr, right. Kr plus Knr is 1 over tau. So, I can have this 1 over tau f minus 1 over tau f, and what other things are there? See here. So, I have excited over here and it can come back from the excited state to the ground state. So, fluorescence intensity will decrease, that is that 1 over tau f is accounted for that. It can move like this way. Then fluorescence intensity of this axis will increase, but this axis will decrease, right, x axis will decrease. So, movement of the molecule from x to y, or movement or rotation of the molecule from x to z, both will decrease the fluorescence intensity along x axis. So, let me write that as rate constant of motion of the molecule from x to y. So, this is again minus, and again this is decrease rate constant of rotation of the molecule from x direction to z direction, right. Now, again I will tell you that the molecule can rotate from x to y, x, y, like this way or that way. So, both clockwise and anti-clockwise. So, in both case I have this 2, and I will take simply take common this minus sign. So, it will be like this to I x t. So, this is my deactivation, but I have said that I have excited with arbitrary polarization of excitation. So, these molecules are excited, these are excited, these are excited. So, though when these molecules are excited, they can also come back to this x axis y to x, then it will contribute to the fluorescence intensity along x axis. So, I also should write this as a plus term over here. So, then I will write here plus 2 k, this is rate constant of reorientation from y to x, right. So, k y to x, and this 2 term I have written again over here because of this clockwise and anti-clockwise, I y t plus from the z to x, right. So, 2 k z x I z t, right. I can write this. Similarly, I can write d dt of I y t equal to, rest follows simply as I said for this d dt of I x t. So, the rest of the things is very similar, I am just writing it over here, k x y I x t minus 1 over tau f. Here see, here this tau f and this tau f, they has to be same because they are same molecule, right, plus 2 k y x, this is from y to x, plus 2 k y z, this is from y to z, I y t plus 2 k z to y I z t, and I can write this as the third one, t of I z t as 2 k x z I x t plus 2 k y z I y t minus 1 over tau f plus 2 k from z to I, this one, right, plus 2 k z x I z t. Right. I got this 1, 2, 3 equations, right. The equation number 1. This time I am putting this equation number because later I need this number for to refer, otherwise it will be difficult to follow. 1, 2, 3. Now, as I said, rotation like this way or rotation this way or rotation this way or rotation that way, they should be same because it is just a solvent and these molecules either rotating in this way or that way. So, this k x y should be equal to k x z, should be equal to k y z, should be equal to k z x, and like that all values should be same, right. So, let us replace these all these values with a one constant, and that constant let us name it as d, right. So, I need to rewrite all these equations, which is difficult, but let me write it. So, d dt I x t equal to 1 over tau f plus 4 d I x t plus 2 d I y t plus 2 d I z t, right. So, here I said that here d equal to all those different k I j's, so which is rotational, diffusion coefficient, right. Let me put as equation number 4, and d dt of I y t is equal to 2 d I x t minus 1 over tau f plus 4 d I y t plus 2 d I z t, let us see this equation number 5, and d dt of z t 2 d I x t 2 d I y t minus 1 over tau f plus 4 d into I z. Let us say this is the equation number 6. Okay, now this d, right, this is rotational diffusional coefficient, right. If you multiply it by 6, right, and you take inverse of that, that is known as tau over. I am not telling from where it is coming, but you take it granted, right. So, you d you multiply it by 6, take this inverse, this is tau over. So, this tau over is called the rotational relaxation time. So, the other equation, this d I can replace with this later on, right, that I will do later on. So, now what I will do, you see here this 4 minus 5, I will do this 4 minus 5, let me do this 4 minus 5. So, equation 4 minus equation 5 if I do. So, linear operator d dt I x t I y t is equal to minus what you will get 1 over tau f plus 4 d, right. Here you get 1 over tau f plus 4 d from this x, and from here you will get 2 d, right. Then I will have minus 2 d whole thing here I x t, and for the I y I will also get this term, but this will be 2 d plus 1 over tau f plus 4 d, right, I y t, okay. Because here you see here minus, I am taking this minus sign, okay. And I will have this z term also, so plus, but they will cancel, you see the 2 d minus 2 d, no. I z. So, if I do it, this will be equal to minus 1 over tau f plus 6 t. So, there is some mistake, yeah, minus 1 over tau f minus 4 d minus 2 d. So, then this should be plus. So, then 6 d to I x t plus 1 over tau f plus 6 t I y t, and here this is nothing, right. So, then this will be equal to minus 1 over tau f plus 1 over tau over. See here this relation, this I took outside. So, then this is equal to I x t minus I y t. Okay. Now, what I will do? I will do the 4 minus, so I have done the 4 minus 5. Now, I will do I can do that x and z. So, then it is equal to 4 minus 6 I can do, right, 4 minus 6 I can do, but before doing that let us integrate this. So, if I integrate, the result will be I x t minus I y t equal to I x 0 minus, so this is the my initial intensity into e to the power minus 1 over tau f plus 1 over tau r to t. So, for this 4 and 5 I got this type of equation. From 4 and 6 I will get this type of equation after doing all these steps. I z t, this will be equal to I x 0 minus I z 0 e to the power minus 1 over tau f plus 1 over tau r into t. So, from here I got what is this I y t, see here. So, this one I will know, from here this one I know. Now, if you put the value of I y t and I z t here and here, you will get everything in terms of I x here, these two will be replaced, I x. So, now let us put that the value of I y and I z to that equation. So, what you will get d d, let me name it as 7, this one is 8, this one is 9, and now putting the value of these two to equation 4, what we will have is d d t of I x t equal to minus 1 over tau f plus this I am writing as 4 d because I did not have this 6 d term which I can replace till now, plus 2 d I x t minus I x 0 minus I y 0 to e to the power minus 1 over tau f plus 1 over tau or t will be here and whole thing will the square bracket, right. So, this is for this y term and I should also write the z term. So, here my 2 d I x t minus I x 0 minus I z 0 e to the power minus 1 over tau f plus 1 over tau r t square bracket close. So, I got this. Now, you can solve it. So, you see this is a big equation. So, I do not want to solve it here. So, I will just write this answer. So, if you solve it, so what you will get is I x t equal to I 0 by 3 e to the power minus t by tau f into 1 plus 3 I x 0 minus I 0 divided by I 0 e to the power minus t by tau r. Simply we will get this, okay, where this I 0 equal to, I should write that, right, I x 0 plus I y 0 plus I z 0. So, similarly you can write for I y t and obviously you can write for I z t. So, I y t will looks like I 0 by similar equation e to the power minus t by tau f 1 plus 3 I y 0 minus I 0 divided by I 0 e to the power minus t by tau r. Here you will get, let me name it as, I have, this is 8, 9, this is 10, then this is 11, this is 12, this is I0 by 3 tau f t by tau f 1 plus 3 IZ0 minus I0 by I0 e to the power minus t by tau r. This is my 13, right. Now, I will put this condition. Now, if my x axis is the polarized excitation, right, and the excitation light is polarized along x axis, then I can simply write Ix, then these are the emission. I am telling if the polarization of the excitation light is along x axis, then Ix will be I parallel, and Iy will be I perpendicular, and Iz will be I perpendicular. That is my condition. So, under that condition, so I am writing if x axis denotes the direction of polarization of the excitation light, and then I can write I x t is equal to I parallel t, and I y t should be equal to I z t is equal to I perpendicular t. So, for this at t equal to 0, so I can simply write this R 0, right, I parallel 0 minus I perpendicular 0 by I parallel 0 minus twice I perpendicular 0. So, here if I assume it like a x, so I can write I x 0, this perpendicular either y or z, let me write I y 0 divided by this is I x 0 and this is I y and I z, sorry this is plus. So, I x plus I y plus I z, right. So, this is nothing but this I 0. So, this is equal to I 0, right. Okay. Now, if I want to calculate this I parallel t, then this is nothing but I x t, right. So, I will simply write this equation I x t. So, this will be equal to I 0 by 3 e to the power minus t by tau f into 1 plus 3 x 0 minus I 0, right. So, now I will write here 3 I x 0, I 0 I will replace with I x 0 plus I y 0 plus I z 0. So, minus I x 0 minus I y 0 minus I z 0 divided by I have I 0, let me write this as I 0 itself e to the power minus t by tau r. So, this is equal to I 0 by 3 e to the power minus t by tau f. So, here you see it will cancel. So, I 0 1 I 0 and this I 0 will cancel. So, 2 I 0 looks like. So, here it is 1 plus 2 I x 0 minus I y 0 and I z 0, but they are same, right. So, I will write here I y 0 2 is common divided by I 0 e to the power minus t by tau r. Here you see I x 0 minus I y 0 by I 0, this is nothing but R 0. So, here I 0 by 3 e to the power minus t by tau f 1 plus 2 R 0 e to the power minus t by tau r. So, I parallelity is telling that this intensity at the parallel to the excitation, intensity of the fluorescence which is parallel to the excitation polarization will decay like this way. I have two term here, one is tau f, another is tau r. Tau f is fluorescence lifetime and then tau r is the reorientational time, right, or orientational relaxation time, right. So, it is like that. Similarly, next day I will calculate this I perpendicular t, and then I will see when I will plug in this I parallel and I perpendicular to my original equation of anisotropy, how the RT will looks like. Thank you very much.